Hi, today's video is about similarity in right triangles. To get started, we're going to define two quick things, go through some theorems, and then do two examples at the end. So the first thing we need to define is the altitude of a triangle. And a triangle actually has three altitudes. So the altitude is the segment. It's actually a perpendicular segment. To a side of the triangle through the vertex opposite that side. Okay, the only reason we need this definition is because it comes up in a theorem here in a second. So basically, if I have a triangle and I pick a side, I'm going to pick that bottom side. I want a segment that's perpendicular to it and it goes through the vertex opposite. So the vertex opposite is going to be that top vertex. So my altitude is going to be this perpendicular. Remember, perpendicular means 90 degrees, right angle. That perpendicular segment through the vertex and perpendicular to that other side. Great. Next definition is a geometric mean of two numbers. We'll call those two numbers A and B. Is a new number, x, such that x solves this proportion. So A over x is going to equal x over B. Okay, so an example of that would be find the geometric mean of 4 and 18. So if I do 4 over x equals x over 18, then my next step would be to multiply, cross multiply, so I get 4 times 18 equals x times x, or x squared. If you hear some noise in the background, I'm sitting on the couch next to my dogs here, so they're both kind of snoozing. So 4 times 18 is 72. That's a terrible 7. So I have 72 equals x squared, and then I'm going to take the square root of 72, and that's going to be the geometric mean of 4 and 18. You're allowed to keep 72 like that. You can keep it as square root of 72. You can plug it into your calculator and give me a decimal approximation. If you know how to do simplest radical form, that would be what I would prefer. So for simplest radical form, I'm going to look at 72, and I'm going to think, what is the biggest square root or perfect square factor of 72? So perfect squares are 4, 9, 16, 25, so on and so forth. So the biggest one that's a factor of 72 is 36 times 2. And you might be wondering, why do I want perfect squares? Well, I want perfect squares because then I can write the square root of 72 as the square root of 36 times the square root of 2, right? So all I did was take these and replace 72 with 36 times 2. And then the square root of 36, we can actually take the square root of, and so now I'm going to get 6 root 2 is going to be my geometric mean. So you can write it as 6 root 2, or you can write it as square root of 72. So if you don't know how to do perfect square or simplify radicals, just leave it as square root of 72. I'm perfectly okay with that. All right, next we have three theorems, and I'm just going to read them, talk about the pictures real quick, and then what we're going to do is we're going to actually decompress all three of these in kind of one statement, okay? So the first theorem says the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. So this theorem is going to be the big theorem you need to know, okay? The other two are little shorthand theorems if you would like, but you don't need to use them, okay? So this one is the goal of today, all right? So what does that mean? That means if I look at this right triangle, the big one, and I draw the altitude from vertex C to side AB, okay, so this altitude here, now I have three triangles. I have a small triangle, I have a medium triangle, and then I have what I like to call the large triangle, okay, so small, medium, and large. And all three of those are going to be similar to each other. So I have that triangle ABC is similar to triangle ACD is similar to triangle CBD, And so what I like to do is I like to divide them up and draw them as separate triangles. So if I was to draw these as separate triangles, I would have triangle ACD, and I'm going to mark my right angle. And then over here, I would have triangle, mark my right angle, CDB. And then I also have the big triangle. The big triangle has the right angle on the top, and that's ACB. And so those are going to be similar. So all of my hypotenuses, the side across from the right angle, are going to be corresponding sides. All of the short legs are going to be corresponding sides. And then all of the long legs must be corresponding sides to each other. So if I put them all together, none of the colors I highlighted should match, okay? Because the short side of the medium triangle is not the same as the short side of the small triangle. So here's my small triangle, my medium triangle, and my large triangle, okay? So then corollary. So corollary, remember, is just a statement that follows directly from a theorem. Our next two corollaries help me set up proportions based on knowing that these three triangles are similar. So if I look at the first one says the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. Okay, that's lots of words, but let's look and see what they did here. So they said AD, so I'm looking right here at the proof statement. So if I know that I have the altitude to a right triangle, I have AD over CD equals CD over DB. So let's talk about where these sides come from. So AD and CD are both on my small triangle. Okay, those come from my small triangle. And CD and DB, these both come from my medium triangle. All right, so those come from this triangle. And then if I look at how they're color-coded, so AD is green, and CD is also green on the medium triangle. And then on the small triangle, CD is blue. And on the medium triangle, DB is blue. Okay, so each fraction comes from one triangle. And the numerators both are corresponding parts. And the denominators are corresponding parts. Okay, so that's what's happening in that one. Now let's take a look at my next one. So my next corollary says the altitude of the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the adjacent hypotenuse segment of the length of the hypotenuse. Okay, lots of stuff going on here. Let's dissect my proportions. So my proportions are AD over AC equals AC over AB. And I also have proportion DB over CB equals CB over AB. Okay, let's look. So AD and AC. Which triangle has AD and AC? Okay, so that would be the small triangle. And then which triangle has AC and AB? That would be the large triangle. And so now if I look on the small triangle, AD is green and AC is yellow. On my large triangle, AC is green and AB is yellow. So my fractions, each fraction is organized by triangle. The numerators are going to be my corresponding parts of the short legs, and the denominators are my corresponding parts of the hypotenuse. Okay? And now I can do the same thing with, instead of the small triangle compared to the large triangle, I'm going to do the same thing where I have DB over CB, which comes from the medium triangle, and CB over AB comes from the large triangle. So let's look at this. So DB is the long leg, and that's in blue on the medium triangle, and CB is the long leg on the large triangle, which is also in blue. And then CB on the medium triangle is the hypotenuse, and AB on the large triangle is also the hypotenuse in yellow. Okay, so all we're doing here is we're recognizing that I have three similar triangles, and I can use that to set up proportions. So you actually don't need to know this theorem or this theorem if you don't want to. They're very wordy. They might be confusing. All you need to know right here is that we have these 3 similar triangles if I have that altitude through the middle of a right triangle. Okay? Let's take a look here. Examples. Solve for x and y. All right, so first thing I like to do is I like to go ahead and divide up my triangles. So x, y, 4, and then over here, so this is my small, here's my medium. I have y, 5, and I don't know. And then on my large triangle, I'm going to put my right angles here. I have 9, right, because 4 plus 5 is 9, and x. So then I'm going to go through and highlight. So I'm going to highlight all my hypotenuses. That's the easiest to identify with one color. Then I'm going to highlight my short legs with another color. Okay, and then I'm going to highlight the long legs with another color. Okay, on this one it's a little hard to tell exactly which one is the short leg and which one is the long leg. So what you can do is you can draw your picture, imagine this triangle a little bit more elongated if you want to, okay, because I know that 5 is longer than 4, and so that can help you identify your short leg and long leg. Okay, so now we're solving for x and y. So I'm going to look at this small triangle because this small triangle has both x and y in it. My medium triangle has only y, and my large triangle has only x. So I'm going to compare my small triangle and my medium triangle to find y. Okay, so let's find y. So if I compare those, if I have on my medium triangle, if I do y over 5, I have blue over green, okay, on the medium triangle. So now I have to do the same thing on the small triangle. I want blue over green. So my blue side is 4, and my green side is y. Okay, and I should only have one variable there, so then I'm going to go ahead and solve. So I'm going to say 5 times 4 is 20 equals y squared. So then I get y equals the square root of 20. Or I can divide that back up into 4 square root of 5 times square root of 4, and then I get 2 root 5. I am okay with either square root of 20 or 2 root 5 as your answer. Okay? Now let's solve for x. Solving for x, I'm going to use the large triangle. And in the large triangle, I have the blue side and the yellow side. So I have x over 9. So the blue side and the yellow side. And then in my small triangle, I want to do the same thing. I want the blue side over the yellow side. So for that one, I'm going to have the blue side is 4 and the yellow side is x. And so then if I go through and I solve that, I get 4 times 9, which is 36, equals x squared. Take the square root of 36. Oh, I got lucky. That's a perfect square. I get 6 equals x. Okay? So there are our answers, and y equals 2 root 5. All right. Let's do one last example.